Now let us see how this all connects to the actual process of doing finite elements. So in finite elements, as you might already be aware, the body that we are analyzing is divided into a number of elements. So these are typically the elements, and they are connected to a number of nodes. Obviously, there are traction boundary conditions specified on certain parts of the body. There are displacement boundary conditions specified on other parts. So once this meshing is done, uh, we forget about the body as a whole and actually analyze the mesh, which is just an assemblage of elements and nodes. Now these elements can be theoretically of any shape, but most often triangular or quadrilateral elements are used in two-dimensional problems, and tetrahedrons and hexahedrons are used in case of three-dimensional problems. So the process of meshing an arbitrary geometry with uh, triangular elements or hexahedral elements is a problem in computer aided design, and there are efficient algorithms, especially for meshing something with triangles or tetrahedrons. There are very efficient algorithms that are available, and that's an issue that we are not going to talk about in this course. So these algorithms are normally part of any finite element routine and finite element code, and you can learn more about them in a CAD program. Now, the basic idea of dividing things into elements is imposing this constraint. Remember, our body has to be in a state of energy minimum, and that's the equilibrium state, and we have to find the u that minimizes the energy, which means that we have to satisfy this equation where pi is the potential energy of the body. And now, since you have divided things up into elements, then you are basically imposing that the summation of the elemental variations, first variations of the elemental potential energies, have to be equal to 0. So this is what we are going to impose, and this is what we are going to look for. Now, this is the potential variation in the potential energy of the eth element, and the eth element has a volume V. It may so happen that that an element may share an edge, an outer edge of the body, and then the total surface surrounding the body is the union of all these elemental edges that make up the surface, and then the total volume is the union of the elemental volumes that make up the entire volume. So this is what we are going to do. We are going to partition the variation in the energy into small chunks that are going to be evaluated within each element. Now, in order to do that, we introduce the concept of something called a shape function. So shape function, depending on the dimension of the problem, may be a function of one variable, two variables, or three variables. And then you have, at every node, you have a set of degrees of freedom. Let's call them u. So u1, u2, and so on are the degrees of freedom. Then each of these u's are represented as n1, let's say u11 plus n2, u12, and so on. This is again written as n1 u21 plus n2 u22, and so on. So here the first one represents the number of the degree of freedom. So this first one we write it with a small I, where I goes from 1 to n, where the number of degrees of freedom at every node is n. The second number, which we write with a capital letter, goes from 1 to capital N, where capital N is the number of elements, number of nodes connected to each element. So if we have a triangular element, and this is an element that we call a linear triangle, we'll learn more about it, then there would be three shape functions, each connected with one node. So what we are doing here is we are trying to we are not trying to solve for u exactly everywhere. We are trying to find the values of u only at the nodes. So if there are three nodes, these and this is a two-dimensional problem, then this is u1 1 and u2 1, then u2 u1 2, u2 2, u1 3, u2 3, where this is node number 1, this is node number 2, this is node number 3. So these are the nodal values of the degrees of freedom. And now if I want to know the value of, say, degree of freedom 1 at this point, which has coordinates of x and y, we will use these three values and interpolate u1 at this point xy using the shape functions. So shape functions are basically interpolation functions which allow you to interpolate at any point inside the element the value of a degree of freedom given the values of the degree of freedom at the nodes in the element. So this is an approximation that we always will make, and this shape function will depend on the kind of elements that you have chosen, the element shape, the number of nodes that you have in the element, etc. So we will look at the forms of the shape function and how these shape functions can be generated somewhat later in the course. But right now, let us look at what properties this shape function must have. Now, one property that the shape function must have is if you write down this for, say, u1 at any point x, y is equal to n1 u1 at node 1, n2 u1 at node 2 plus n3 u1 at node 3 and so on. Supposing that there are only three nodes in the element, we are looking at this kind of element and there are just three nodes. In that case, if I put the coordinates of, let's say, node 1, so if I write u1 at x1 y1, where x1 y1 is the coordinate of this point, then I must get u11 because that is the value of u at the nodal coordinate x1 y1. Similarly, I should get u2 u1 x2 y2, where x2 y2 are coordinates of this point. That should give me u12, and then u1 at x3 y3 should give me u13. In order for that to happen, these functions must satisfy what is known as the Dirac delta property. And the Dirac delta property says, it says just this, that ni at xj must be equal to delta ij. So if that means that ni at the node I, at the location of the node I, ni evaluated at the location of node I should give me 1, and ni evaluated at the location of any other node should give me 0. See this clear again, we can see this clearly with the three-noded triangle, let's say. So this is node 1, node 2, node 3. This is x1 y1, x2, y2, and x3, y3. Let us look at the value of, say, u1 at node 1. Its value is u11, then it is u12 and u13. So at any point inside, u1 xy will be n1 u11 plus n2 u12 plus n3 u13 for this three-noded triangle. Now, if I want the value at, let's say, u1 at x1, y1, then n, remember, is a function of xy, n2 is a function of xy, and n3 is also a function of xy. So n1 at x1, y1 is 1. N2 at x1, y1 is 0 by the Kronecker delta property. N3 at x1, y1 is 0 as well. So if n1 is 1, then this becomes equal to u11 as it should be. Similarly, if I want u1 at x2, y2, then n1 at x2, y2 is 0, n2 at x2, y2 is 1, n3 at x2, y2 is 0 again. So I get n12. So just to ensure the fact that this interpolation gives the correct values at the nodes, we must make the shape functions satisfy the Kronecker delta properties. That means ni is 1 at the location of node I, has to be 1 at the location of node I, and has to be 0 elsewhere. The other property that the shape function must satisfy is that of partition of unity. And that is because this interpolation here must work if in the most trivial case, this is a constant function. Let's say it's a constant equal to C naught. Then the values at the nodes are also C naught. So this has to be C naught as well. And if this has to work in that situation where the value of the field variable is a constant all over the element, then the C naught cancels and summation of all the ni's must be equal to 1. This is known as the partition of unity property. That means that shape functions for an element, so there are as many shape functions in the element as there are nodes, so the shape functions for the element must sum up to 1. So these are the two properties, the Kronecker delta property and the shape function partition of unity property are the two important properties that all shape functions must satisfy. Now given these things, how do shape functions look like? What kind of functions are the shape functions? So if you take a 1D domain, for example, so this is your domain, and you have meshed it up into a number of nodes, and these are your elements. So each of your element has 2 nodes, and therefore there are two shape functions per element. And the first shape function, let's take this element as a representative element. This is 1 and this is 2. So at node 1, shape function n1 must be 1, and at node 2 it must be 0. So it's a linear function. It has to be a linear function because there are only 2 points from which you have to determine the shape function. So it has to be a linear shape function that goes from 1 at node 1 to 0 at node 2. Similarly, the shape function n2 has to be 0 at node 1 and 1 at node 2. So it will go the other way, and it will again be a linear function that goes from 0 to 1. In a two-dimensional domain, say a two-dimensional domain that is broken up into 4 elements. These are the 4 elements, 1, 2, 3, and this is 4. These 4 elements, then each of the shape functions, so this is 1 at this node, 1 at this node, and 0 everywhere. So it's kind of a tent-like function which has to go to 0 at these nodes, and if there are no nodes in between, then it has to go linearly. And similarly, this shape function is 1 at this node and 0 at these nodes, and so on and so forth. So you will have these tent-like shape functions, tent-like shape functions with linear edges for typically for three-noded triangular elements. For four-noded quadrilateral elements, you can imagine how the shape functions are going to be. So if I take a four-noded quadrilateral element like this, and these are the nodes 1, 2, 3, and 4, then the shape function n1 has to be 1 at node 1, and it has to go to 0 at nodes 2, 3, and 4. So this would be the surface of the function that will constitute n1xy. Okay, so these are the two properties of shape functions which we will use to determine shape functions in first in case of problems which we have already done by other means, namely the bar and the beam. We will revisit the bar and the beam and try to now derive the stiffness matrix for the bar and the beam based on the concept of shape functions, number one, and number two, from an energy perspective, from the perspective of minimization of energy, starting with a weak form. That's what we are going to do now.